and thank you very much for the invitation to speak here. So I'm going to speak about a joint work with essentially it's Luca and Yassine Chitour. And I'm going to speak, as the title says, about Weyl law for singular Riemannian manifolds. So what's that? Okay, let's start by speaking about the Weyl law in Riemannian manifolds. Okay. So I'm going to consider here Riemannian manifold M, let's say with a smooth boundary. It could be that the boundary is empty, doesn't really matter for the moment. And what I'm interested in, well, of course, I will endow this with a Riemannian metric and with the Riemannian volume associated with this metric. Okay? So once we have our manifold and a Riemannian metric, by using the Riemannian volume, we can define the Laplace-Beltrami operator for this manifold. Okay? So that's going to be simply, I would call it delta, and it's going to be simply the divergence, as Fabrice says, of the Riemannian gradient. Okay? So here, what I get in general is an operator that is a symmetric operator on L2 of M with respect to the Riemannian volume. And its domain, we can begin by saying it's smooth compactly supported functions on M. Okay? Now, a very classical result for this operator on a Riemannian manifold is that if we consider delta plus some boundary conditions, let's say Dirichlet conditions or Neumann, it's not gonna matter. In this case, we get a self-adjoint operator, an essentially self-adjoint operator. Okay, this yields an essentially self-adjoint operator. And if M is compact, this essentially self-adjoint, well, the self-adjoint realization of this operator is going to have discrete spectrum, okay, that accumulates at infinity. So we have the spectrum is a sequence of number that goes to infinity, if M is compact. So let's assume our manifold is compact. We have smooth boundary. We fix these boundary conditions. And this allows us to define the Weyl counting function, finally. That is simply n of lambda, which is the number of eigenvalues that are below the threshold lambda. So we fix an energy level, we count how many eigenvalues we have. And the interesting thing here is that, well, that's the celebrated result by Weyl essentially, but later generalized to Riemannian manifolds, is that this n of lambda behaves asymptotically as lambda goes to plus infinity, as omega n over 2 pi power of n, I think, times the Riemannian volume of M times lambda to the power n and a half. Okay, so here n is the dimension of the manifold. Omega n is the volume of the Euclidean ball of radius 1. And here we see the Riemannian volume of the manifold. And the power of lambda we get depends on the dimension of the manifold. Okay, so we have a lot of geometric information simply in the asymptotic expansion of this n of lambda. Okay? An interesting fact that I will not use is that if we build the Laplace-Beltrami operator with a different measure, we still get the same Weyl law with the same Riemannian measure here. Okay? It doesn't depend on the measure we fix. So now, the main question that we're interested in, the main problem that we're interested in is what happens if the metric G is singular in a specific sense on the boundary. Okay, now I implicitly assume that this metric G was defined up to the boundary in a smooth way. What happens if this is not the case? What happens if there are some terms in G that explode or go to zero, for example? Now, what's the motivation of this question? Let me present you a simple example. Maybe we'll clarify why we are interested in this kind of things. We will be able to say. So let me start by speaking about an example. That's going to be the Gaussian structure on the sphere, so the Gaussian sphere. Okay, this is what we call an almost-Riemannian structure that I will introduce later in more generality, but what happens is the following. So we consider S2 as a submanifold, S2 in R3, essentially. Okay, so let's see if I can. We have this picture. Here we have our coordinates, x1, x2, and x3. And we consider the generators, the vector fields x1 and x2 that are the generators of the rotations along these two axes. Okay? Now, these two vector fields are not collinear. X1 and x2 are parallel. Say, like these are parallel on what will be the singularity of our metric, that is simply the equator x3 equal to 0. And on this manifold, so on S2 minus Z, I consider the metric G such that x1 and x2 are orthonormal. Are an orthonormal frame. Okay? So this is a Riemannian metric on S2 minus Z that's singular on the equator. Okay, what's the expression of this metric? So maybe we can write it a little bit better. So let's see. We have our sphere. We can build essentially coordinates in a neighborhood of the equator that are going to be coordinates of this type, are going to be coordinates, I will take coordinate t that runs between minus epsilon and epsilon, and the coordinate theta that lives on S1. Okay, this is going to parameterize a neighborhood of our equator. And if we consider these coordinates, we can make an orthonormal change of variables, and we get that the metric generated by x1, x2 is actually the same one as the one generated by x tilde 1 that is going to be t, and x tilde 2 that is going to be t d theta times some smooth function that depends only on t. Okay, here phi is a smooth function of t. Okay, so we represent this as a cylinder. Here we have t, and here we have theta. And so this, what does it mean on the metric? This thing means that our metric in these coordinates is going to be something like this. So you see that our metric, when t is equal to 0, so when we get to the equator, is exactly, well, it becomes deeply singular. Okay. Now, as a consequence, we have that the Riemannian volume is something of this type. So it explodes, the Riemannian volume. So every set that crosses the equator is going to have infinite volume. And the Laplace-Beltrami operator, we can write it in these coordinates, is something like t squared plus t squared e over 2 phi theta squared. And here we have minus, it should be, I think, something like this. So we have an operator where we have one term that goes to 0 when t is equal to 0, and one drift, a first order term that explodes when t goes to 0. Okay? Now the interesting thing about this fact, this manifold, well, this has been already studied by many people for different reasons, but what is interesting for us is a result by Boscain and Laurent that tells us that this operator, that we can begin by defining it only on C infinity C of S2 minus Z, so we have to choose functions that are supported away from the singularity, otherwise this term is going to pose some problems. And Boscain and Laurent proved that delta is actually essentially self-adjoint on L2 of S2 with its Riemannian metric. Okay, so we do not need actually to pose any boundary conditions on the singularity. Okay, these are automatic due to this term that pushes us away from the singularity, that brings us to the singularity. Sorry. So what we have proved, on the other hand, with Ugo and Marcello, is that in this case we can compute explicitly n of lambda due to the symmetries, essentially, and we get that the leading term is something, if I'm not mistaken, something like 1/4 lambda log lambda. Okay, so here we are on a 2-dimensional manifold. If it was a Riemannian, we would expect something like a constant times lambda, because n divided by 2 here is 1. But we get an extra logarithmic term, okay, for this manifold. Well, that's strange. And so this is something that is called non-classical Weyl law, sometimes in the literature. And so our aim is essentially to understand why this is happening, what are the things at play here, and especially what's the meaning of this term. Okay, we assume that we will show that it's actually the singularity that adds some eigenvalues, and in some cases we will be able to determine what is the geometric meaning of this constant. Okay, so this is an example, an explicit example in which we can do computations. And let's see what we can say more in general. So I won't present the full result because it takes a lot. I will simply restrict myself to the case of almost-Riemannian geometry here, and then maybe say some words on what we can do beside this Riemannian. Okay. Now, almost-Riemannian geometry is something that generalizes this. It can be seen as a subset of sub-Riemannian geometry in a large sense. And essentially what we will do is the following. So we will consider some compact manifold M with no boundary. Okay. That's going to be our ambient manifold, as the sphere was before. And I'm going to fix a singularity Z that's going to be an embedded smooth hypersurface where the metric that I'm going to choose is going to degenerate. Okay? I will consider G a Riemannian metric on M minus Z. And I will assume the following that it has a certain behavior around Z. So I will assume that before, if I parameterize this part of my manifold as minus epsilon epsilon with a coordinate t, let's call it x, times Z, here my metric is gonna be essentially I don't want to say something false here. Yeah, exactly. I'm not going to write the metric. I'm going to say that here we have an orthonormal frame that's going to be simply x0 equal to the x. So we have always one vector field that goes in this direction, and certain vector field xi that are going to be some for j from 1 to n minus 1, where n is always the dimension of certain functions that depend on x and z, of dzj, where dzj are simply a basis for the tangent vectors of z. Okay, this is just local. We'll assume that this is an orthonormal frame, and of course, for everything to work, I will assume that this things degenerates on the singularity. So we'll assume simply that the determinant of this aij is going to be 0 if and only if x is equal to 0, that is, we are on z. Okay? So we'll take a Riemannian metric that degenerates exactly on z. And okay, this is essentially what it is in almost Riemannian geometry in some large sense. Here, for whom of you who knows, I'm restricting myself to the case where we don't have any tangency points, okay, any characteristic points where these vector fields could become tangent to the hypersurface Z. Okay, this I'm going to exclude for the moment because it doesn't work. And moreover, okay, just to simplify everything, I will suppose that we are in what we call a strongly regular, almost Riemannian structure. By strongly regular, I mean that I can write that there exists M such that my functions aij xz can be written as x to the power of M times certain functions aij hat such that the determinant of my aij hat is always different from 0. Okay, so I can desingularize my vector fields by taking out an x to the power of M that is uniform, it's the same for all vector fields. So if you want here, I'm saying that I can write xi as x to the power M xi hat. Okay, where xi hat is a family of linear independent vector fields. Okay? What's interesting here is that we can say something about the volume. Yeah. Under this assumption, we can say that the volume is essentially up to a smooth function, something of this type. So it explodes like x to the power m n minus 1 when we fix some reference measure and up to a smooth function here. But the explosion here is exactly this one. Okay? And the fact that the volume explodes is actually the most important fact here for us, at least for the technique we apply, because that's going to be what really dominates. So let me just state the theorem, then I will discuss it. Okay, so first of all, we can prove that under these conditions, we have that the Laplace-Beltrami operator is essentially self-adjoint and has discrete spectrum. So we can speak about the Weyl counting function. Okay, this is a result actually got with well, myself, Luca, and Marcello. Okay, once we have this, so we know that we can compute the Weyl counting function, and we get the following for the asymptotic. Then we have, if we are in dimension 2 and m is equal to 1, that is the case, for example, that we had before, then n of lambda is not equal, but is equivalent as lambda goes to plus infinity. I never remember the constant here, but yeah. Is equivalent to the volume of the singularity, to the regularized volume of the singularity that I will explain soon what it is, times lambda log lambda. Okay, so we have a way to define a regularized volume of the singularity, and this is what is going to appear here. And in fact, in the case that I presented before, the singularity was just S1. This regularized volume is just 2 pi, and we get 1 over 4. Okay, but I will come back to this in a moment. Otherwise, well, in the other cases, we cannot say anything about the constant, but we just get the asymptotic behavior in lambda, and we get essentially that there exists a certain constant positive such that 1 over this constant is smaller or equal than n over lambda to the power d and a half, that is bounded by this constant, where d, I never remember the exact expression in this context, is n minus 1 times m minus 1. Okay, so just to say here, you see if we have m strictly m plus 1 probably. Yeah. If we have m equal to 1 and then equal to 2, we get that d is equal to n. Otherwise, this number is strictly bigger than n. Okay? So it's something like the dimension, the actual dimension of our singularity here. And in fact, it's exactly that, because, just to remark, that this number d is what is called the Minkowski dimension of the singularity. Okay. So d is the Minkowski dimension that is, what we do is that we have z, you want to compute the Minkowski content, the Minkowski dimension of something, you know that you have to take it, you take a neighborhood, an epsilon neighborhood, and you compute its volume. And then you see how this volume goes to 0 as epsilon goes to 0. Okay, here we cannot do that because the volume is infinite of this thing. So we compute the volume of something like this, okay? We take something at distance epsilon and 2 epsilon, and then send it to 0 and see how it goes to 0, okay, or it explodes. And that exponent corresponds exactly to d in this context, in this context. And then what I denoted by the regularized volume of z is simply the integral over z of e to the power phi, essentially z. So you see here we have our Riemannian volume is e to the power phi divided by this. We simply take out this component here, so that we desingularize the measure, okay? And this can be defined intrinsically as the Minkowski content with respect to this definition of Minkowski dimension, okay? What do I have to say still? So as I told you, this quantity in the Grushin sphere, this quantity is equal to 2 pi, and so we get our result. And what we have, so what I want to stress is that in the case where m and n are not equal to 1 or 2, we have no information on the constant. And this technique it's probably the technique that I'm going to explain, the technique that allows us to recover this theorem, is probably not sufficient to get the constant there, because we actually, what we are doing, and what I will explain in a moment, is that we are cutting out our singularity from the manifold and doing a limit procedure. So we do not see the structure of the vector fields, the structure of the metric around exactly on the singularity. Okay, we lose that, and probably in this case the constant, well, our conjecture is the constant in the Weyl law is connected with the nilpotent approximation, or if you want, the structure of the Lie bracket on the singularity. And we are not able, this technique will not allow us in any way to read this at any point. Okay? And also I want to remark that this result was announced in the case of n equals 2 and m equals 1 by Emmanuel and Yves and Luc Hilaret. For the case n equals 2, m equals 1, and where they consider a measure that is not singular, that is smooth. Okay? And they get exactly the same result, up to some notation, but it's exactly the same result, which is, well, which could be reasonable or not. I have no idea. Yeah. So, I wanted just to finish by talking a moment about the strategy of proof. So what do we do exactly to prove this result? So the idea, as I told you, is to cut out the singularity and exploit the Riemannian Weyl law. Okay, so we know, okay, let me define this. Okay, let's say that delta is the distance from the singularity with respect to the metric. Okay, we can define this quantity. And what we can prove is that under our assumptions, delta is actually smooth on a set where delta is smaller, for example, than a certain epsilon 0. Okay? So delta is a smooth distance. We use that to build coordinates. And I will define following. So m0 epsilon is gonna be simply the manifold where delta is smaller or equal than epsilon, the part of the manifold where delta is smaller or equal than epsilon. So it's gonna be this part here. And m epsilon infinity is gonna be the part where delta is bigger or equal than epsilon, so it's going to be here. Okay. Now, if epsilon is sufficiently small, m epsilon infinity is a Riemannian metric, is a Riemannian manifold with a smooth boundary. Okay, both of these are Riemannian manifolds with smooth boundary. Okay. So we can apply, at least here, no, this is not a Riemannian manifold, sorry. This is a Riemannian manifold with smooth boundary. This is not Riemannian because we have the singularity. So here we can apply the Weyl law. Okay. But there are some hiccups. So the main technical tool at this point is to do the following. So we first apply, it's called Dirichlet-Neumann bracketing. Okay, the Dirichlet-Neumann bracketing allows us to compute, to estimate the full Weyl law by the Weyl laws on these two parts of the manifold. So it tells us essentially that our n of lambda is smaller or equal than the Weyl law on m0 epsilon with Neumann boundary conditions. This plus stays for Neumann boundary conditions, plus the same thing on m epsilon infinity, and is bigger or equal than the same thing with Dirichlet boundary conditions. Okay? Okay. So now the point is that here we can apply, well, we should be able to apply a Riemannian by law. Okay? So now the first thing to do is to kill this term, essentially. And what we have is that, well, second step is that we know that on the boundary of this manifold, okay, so when delta is equal to epsilon, in this type of structures, we are mean convex. We are actually convex, but it's sufficiently mean convex, because mean convex allows us to prove an hard inequality which essentially amounts to saying that n of m0 epsilon plus or minus on lambda is equal to 0 if lambda is smaller than 1 over 8 times epsilon. Okay? So if lambda is small, we do not have any eigenvalues. Okay? So this means that if epsilon goes to 0 sufficiently fast as lambda grows, we will not see this term here. Okay? And then the last point, that is the crucial point here, so this thing tells us that we could choose epsilon depending of lambda as a certain constant divided by the square root of lambda. Here there is a square. Yeah, here there is a square. Yeah. This is going to imply n of lambda is more or equal than n of m epsilon lambda infinity plus, and the same thing here. Okay? And now when we send lambda to infinity, we would like to recover the same expansion here and here, and to be able to control this. Okay? The problem is that the Weyl law that I stated before depends, has some hidden constants that depend on the manifold, essentially. Okay? So the crucial point is that we have to derive a Riemannian by law, a new Riemannian by law, let's say, where we do the following. So, okay, let me say before of this, so this n plus or minus m epsilon infinity of lambda, we know by the Riemannian by law already that it's something like this. So it's omega n over 2 pi over n, the volume of m epsilon infinity times lambda n and a half. And here we have a certain remainder that depends on epsilon, that is depends on the manifold and depends on lambda. And the only thing that tells us the Riemannian by law is that this term goes to 0 and lambda goes to infinity. So what we do is that we derive essentially bounds on this term that depend only on certain Riemannian quantities of our manifold. And essentially these quantities are, it depends only on bounds, essentially on the sectional curvature, on the Rizzi curvature, on the Hessian of the distance from the boundary, and let's call it distance from the boundary, and the dimension n. Okay? So we connect how this thing goes to 0 to bounds, specific bounds on these quantities. And since we will be able to control these terms, we will be able to pass to the limit, essentially. So just be a little bit more precise here. and say that in this context, we have the following. We have the dissectional curvature of m epsilon infinity is bounded by a constant divided by epsilon squared. And the Hessian of the distance from the boundary is bounded, is smaller than 0 and bounded from below by a certain constant divided by epsilon as epsilon goes to 0. So these quantities explode, but in a specific way depending on epsilon. And this tells us, by applying that result, that I didn't write, something like R epsilon of lambda behaves, it's controlled by a constant times epsilon squared times lambda over minus n over 2. There's something of this type. Okay, so due to these bounds, we recover some bounds on this R epsilon of lambda that depends on the product between epsilon squared and lambda. Okay, and you see that if I choose epsilon lambda like this implies that my R epsilon of lambda is bounded by some constant, maybe bigger. Okay? And thus I can plug this thing here and here, pass to the limit, and this is going to go to a constant, while this term is going to give me the additional power of lambda, okay? Because in this case, I have the mu g of m epsilon lambda infinity, that is epsilon lambda power of minus m times n minus 1 plus 1. This is equivalent to lambda to the d minus n over 2. Okay, and so we get, from the explosion of the volume, we get what was missing in the eigenvalues, essentially. Okay? So this is the result in the almost-Riemannian case. Actually, the result is more general than this. It applies to any Riemannian manifold where you have a singularity, the Riemannian manifold is compact, and these conditions are satisfied like this. Okay, so you know that when you go to what is your singularity, what is your boundary, your Riemannian quantities are exploding in some ways like this. Okay, this is what is actually necessary. So convexity, this bound from below and this bound from above of the modulus of the sectional curvature. Okay, that's all it is. And the technique to prove these inequalities actually comes from a Karamata type lemma. So we actually estimate precisely the heat kernel along the diagonal of our m epsilon. Okay, we estimate carefully this heat kernel depending on these quantities, and then by using this Karamata type lemma, we can recover from the heat kernel, from the heat trace actually, the Weyl law here. Okay, and then just to finish, in order to get this result for n equal 2 and m equal 1, here you have to use a small trick, simply to divide your manifold in 3 parts and exploit the fact that at this point, in that case, here you get a logarithm. Okay, and so you can play around with the fact that the logarithm of an exponential of some power. You play around with the fact that here in this case you have the logarithm of epsilon lambda, essentially. Okay, that's, and yeah, that was what I wanted to say. I think I'm finished. I don't know if we are.
No other questions? Questions, remark?
Well, yeah. Yeah.
Yes. Yes.
But in the ratio then n lambda over lambda, Is there a limit or that's the...
No, that's for sufficiently big lambda.
Yeah, but do you know if for lambda that goes to infinity, if there is a limit?
No, that would be, if we knew that, we would have an asymptotic expansion of this type. We don't know. We know certain things about this C, but it's really not sharp at all, so we cannot say much, essentially.
Okay.
Yeah, because essentially there is this constant here that we do not know, and so you cannot say much with our technique.
If it is possible to explain it in few words, could you elaborate a bit on what kind of information, what kind of more precise information do you need on the heat kernel along the
So here what we get here is simply, let me see if I have, I've written something. Essentially what we have is that if you have your manifold and you know that your sectional curvature is bounded by from above by a certain k, and your Rizzi curvature is bounded from below by minus n minus 1k, and then you have also this bound on the Hessian of the distance from the boundary. This is not, could be also like this. Then what we have is something of this type, so here I don't want to be. So you have the integral of ktxx. So you know that the heat trace minus 1 is bounded by, essentially what we can say is bounded by kappa times t, plus here you have the volume, the surface volume of the boundary of your manifold with boundary. This m here is what was m epsilon infinity here. Okay? And here you have the volume of your manifold. Here you have the square root of t. Plus here you have an exponential term of this type, where here you have some quantities that depends on the injectivity radii on your manifold. And this formula is valid for t sufficiently small if it is smaller than, essentially, let's say the minimum between the injectivity radius of the manifold and pi over square root of k and 1 over h. Okay, so for sufficiently small t in this sense, we get this bound. Okay, and that's something like this that we need, more or less. Okay, well, exactly this that we need to exploit our techniques. Yeah.
This holds for a given fixed Riemannian manifold.
This holds for a given fixed Riemannian manifold. Yeah? Then you replace h with h over epsilon, that is your thing that is exploding, and you see that you can control the explosion of the terms. Okay?
Can you also see the off-diagonal terms?
For the diagonal terms, we could say something, but it's much more complicated, and we decided not to go too deep down there, because what is difficult for the off-diagonal terms is to understand, if you have just ptxy, to understand what exactly you have to put in place of the 1, and it depends a lot on the curvature and everything. So we didn't look too much into that since we didn't need.
Other questions? So if not, we think again the speaker.